Okay, so let's look at our next section, which is 6.5, and we're going to talk about the central limit theorem. The central limit theorem is extremely important in statistics, and it basically allows us to do what we want to do. It allows us to use sampling to make assumptions about the population. So what it means is any distribution of sample means approaches normal as the sample size increases. And that is true whether the population is normal or uniform or very non-normal. And this is the foundation for estimating population parameters and hypothesis testing, which is the rest of this course. Now, a random variable, which we'll call x, has a distribution, and the distribution has a mean and a standard deviation. Well, you know that already. We select a simple random sample of a certain size. The distribution of the sample means will approach normal as the sample size gets bigger. And here is the kicker, and this is one of the most important things. The standard deviation of all the sample means is the population standard deviation divided by the square root of the number in the sample. And we'll look at a picture of this in a bit. Now, the practical rules. If your sample size is greater than 30, then your distribution of your sample means will be reasonably normal, no matter what the shape of the original distribution. And if the original distribution is normal, then any sample size works. Now, notation. This stands for the mean of the sample means. And the mean of the sample means is equivalent to the mean of the population. In other words, the mean of the distribution of sample means is an unbiased estimator of the population mean. The standard deviation of the sample means is equivalent to the population standard deviation divided by the square root of the number in the sample. And this is because averaged data is less variable than individual data. And this is extremely, extremely, extremely important. So no matter the shape of the population distribution, the sampling distribution approaches normal as the sample size gets larger. So for example, here we have our original distribution, and this is sample size of 1. And then we're going to change our sample size of 10, and you can see that what we're going to do is we're going to take 10 individuals from our population. We are going to find the mean, and you can see that that's kind of normal. And we're going to increase our sample size to 50, and you can see we're still normal. And again, this is because average data is less variable than individual data. That is extremely important. Now we have a uniform distribution. So here's our uniform distribution, and we take samples of size 10, and you can see that it gets kind of normal. We take a bigger sample of 50, and it's very normal. And again, this is because average data is less variable than individual data. And even when we have a very non-normal distribution, this one's kind of the opposite of normal. Can you see when we have sample of size 10, our sample means become normal. So that means we'll be able to use the normal distribution to make assumptions about these populations. So again, as sampling size increases, the sampling distribution of sample means approaches a normal distribution. This is part of the reason why statisticians use sampling. It's always best when you're designing a study to use the largest sample size that you can afford. And that sounds kind of funny, but getting your samples sometimes takes money, but it takes time, and you have to be able to find people who fit your criterion. Okay, so here we have an applet that'll demonstrate what I'm talking about. So what this histogram shows is the results when I have rolled one die 10,000 times. If I change it to 2 dice and I do 10,000 rolls, and what I'm going to do is I am going to add the number of spots showing, and you can see if I roll 2 dice 10,000 times, I get kind of a triangular shape distribution. If I do 3, you can see it's starting to become a little bit more bell-shaped, and if I do 4, it should be even more bell-shaped, and if I do 5, it becomes very bell-shaped. So as my sample size gets bigger, even though I would start out with a uniform distribution, my sample means will become more and more normal. Let's start and let's do an example. So we have an elevator with a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assuming a worst case scenario in which the passengers are all male, what are the chances that the elevator is overloaded? We're going to assume that male weights follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. Find the probability that a randomly selected male has a weight greater than 156.25 pounds. That's A. And then for B, we're going to find what's the probability that a sample of 16 males have the mean weight greater than 156.25 pounds. And the 156.25 pounds is the 2,500 pounds divided by the 16 passengers. So to find the probability that one randomly selected male has a weight greater than 156.25 pounds, we're going to do exactly what we did in section 6.3. So the first thing we're going to do is take our weight and we are going to convert it to a z-score. And then we're going to take our z-score and we're going to take either that to table A2 or we're going to take it to our z-score calculator, and we want to know the probability that that male has a weight greater than 156.25 pounds. So if you're going to use the table, you're going to look up the negative 0.65 as your z-score. You'll find this probability down here in the left tail, but we want to take that -1 to find the probability of greater than. And you see that we get the area of 0.7422. Now, how do we interpret that? We interpret that to be that there is a 74% chance that one individual male will weigh 156.25 pounds or greater. Let's look and see how we would do this same problem by hand. So again, we have a normal distribution of weights where the mean is 182.9 and the standard deviation is 40.8. And I'm going to draw that. And so my mean is here. And our question says, what is the probability that x will be greater than 156.25? Well, 156.25 is going to be less than one standard deviation below the mean. So that's going to be down here somewhere. And remember, probability is equal to the area under the curve, so I'm going to look for the area to the right of that. Now, I am going to go to my StatCrunch calculator. Okay, so let's look at the StatCrunch calculator. There's two ways we can do this. We can do the standard z-score, and if you remember from the slides, the z calculation for 156.25 pounds was a negative point, this is a negative 0.65, and we get 0.74215389, which is just a little bit different than what they got, but it's just fine. If we go back to the problem here, we can also do it with the distribution as it stands. We could put in the mean of 182.9, and we could put in the standard deviation of 40.8, and we could say what's the probability that our x will be greater than 156.25, and we can do that computation, and you can see we get the same answer. So it doesn't matter if you do this calculation with your distribution as it stands, or if you standardize it, you will get the same score. You just need to be consistent. Let's go on with okay, so on the StatCrunch calculator, we find that this area right here is going to be 0.7431 or 32, going out 4 places. It's a little bit different than what they got from the table, but that's okay. So what we say here is there's a 74% probability that an individual man, or that one man, will have a weight of 156.25 pounds. Now I'm going to go keep going, and let's go on and do the second half of the problem. And the second half of the problem says if we have a sample of size 16. So this is A, this is B. So n equals 16. And so now we want to know what's the probability that our sample mean will be greater than or equal to 156.25. Well, now our standard deviation changes. So we still have a normal distribution because our original distribution was normal.
our mean is still 182.9, but now our standard deviation has changed to be 40.8 divided by the square root of 16.
Now that standard deviation changed because now we're dealing with a sampling distribution rather than the population distribution.
Or it's normal with a mean of 182.9 and a standard deviation of 10.2. So again, I'm going to draw my curve, and in reality my curve is going to be a lot skinnier and a lot taller. Now how you draw yours doesn't really make much difference, but I wanted to show you that. My mean is still 182.9, but now my standard deviations are much smaller, and 156 is going to be further from the mean, so it's going to be more standard deviation units away. And again, it's a mean, so x bar equals 156.25. So let me do this, and let's go back and let's go ahead and calculate a z-score. So z equals my mean minus the mean of the sampling mean, or the population mean, 182.9. I'm going to divide that by the new standard deviation. And so now it's a negative 2.61. So it's a lot further down the distribution. It's further away from the mean. Remember when we were up here in part A, that z-score from the slides was a negative 0.65. So we go to our calculator. So when we're doing the z-score, we're looking for what's the probability that our z-score will be greater than or equal to a negative 2.61. And on our
So on the calculator, let's go back to the standard normal. So my mean is 0, my standard deviation is 1. And I want to calculate that my z-score is greater than a negative 2.61. And when I do that, I get 0.99547289.
calculator or on the table, we are going to find that probability to be 0.9955 rounded to 4 digits. So we can say 99.55% of the time a sample of 16 men will have a mean weight of 156.25 pounds or greater. Now, let's go back to our problem, because we want to know about the safety of this elevator. So if we have 16 men on this elevator and its maximum weight capacity is 2,500 pounds, chances are high that the elevator will exceed the safe capacity. So since the elevator let's change that to will probably. When 16 men are on board. We may need to lower the capacity. To maintain safety.
So let's go back to our slides here, and I just want you to see how the slides are drawn. So here's our first distribution when we are looking at one randomly selected man. Notice that on the next slide we're dealing with a sample of size 16. And notice this distribution is at the same scale, and notice how skinny it is and how tall it is, because what happened was the mean stayed the same, but the standard deviation was cut by a factor of 4, the square root of 16. And again, here is, I'm going to go back to this one. This is the work that we just got done doing in the pencast, and we came up with the same z-score. And then on this slide it tells us we got the same probability and we got to the same conclusion. They wrote it just a little bit differently on their slides. But on the next slide I just want to compare. The short fat distribution is the distribution for one individual. The tall skinny distribution is the sample mean of 16 individuals. And you see how most of the scores are so much closer to the mean. And this is why we do sampling, and this is what makes it useful for us for statisticians. So what have we done in this last section? Well, we have discussed the central limit theorem, we've practiced rules, and we've looked at what sample size can do for us. What I'm going to do next is do a few problems for you, and I will tell you what page and which numbers they are so you can follow along in your book, so you have a sample of how to approach these types of problems.
Okay, let's do number 16 on page 320. And we're dealing with M&Ms again, and they tell us that the mean weight of M&Ms is 0.8565 grams, and they have a standard deviation of 0.0518 grams. Now, it says that the data came from packages containing 465 candies, and said that the net weight of the package was 396.9 grams, and that came out to be, that's where they got the 0.8565 grams for each candy. So basically we are going to assume that these are normal, and so our mean is 0.8565 and our standard deviation is 0.0518, and these both have units. Now, part A says, find the probability that one M&M weighs more than 0.8565 grams. So again, I want to draw my distribution and see what I'm looking for. So let's draw our distribution. And my mean is going to be 0.8565. And I basically want to look and see what the probability that it's going to weigh, oops, I didn't pay attention here, 0.8535 grams. So that's going to be slightly below. And we're looking for the area above. So what's the first thing we're going to do? We're going to standardize. So what's the probability that Z will be greater than, and that'll be 0.8535 minus our mean, which is 0.8565, divided by our standard deviation, which is 0.0518. Which translates what the probability that Z will be greater than. So the probability that Z will be greater than a negative 0.0579058. If you're going to use the table, it only goes out to two places. So if you're going to use the table, you would use Z as greater than a negative 0.06. But we're going to use our calculator, so we're going to go with this Z-score. Alright, so let's go to the calculator. And we get 0.
So when we go to the calculator, we've already got it standardized. We'll put this in here as a negative 0.058, and we will look for the probability.
Five, 2, 3, 1. So I always like to put my answers in a sentence because it makes the numbers make sense. So 52.31% of the time, one M&M will weigh more than 0.8535 grams. Okay, then part B says, what if 465 M&M plain candies are randomly selected? Find the probability that their mean weight is at least 0.8535 grams. Alright, so now the number in our sample becomes 465. And we want to know the probability that the sample mean will be at least. So at least means or bigger. And that's 0.8535 grams. Now, because we're dealing with a sampling distribution, our distribution is now still has the same mean, 0.8565, but now our standard deviation is going to be 0.0518 divided by the square root of 465. Now you can leave it like that, but I really like to change it. It makes a lot more sense to me, and using the calculator on StatCrunch, I don't think it'll do the calculations for you. So the value of my new standard deviation is 0.0024 grams. So now let's calculate our z-score. What's the probability that the z-score will be greater than or equal to 0.8535 minus 0.8565 divided by my standard deviation.
And now when we go back to the calculator, again, I have my mean at 0 and my standard deviation at 1, so it's my standard normal curve. And I'm going to put in my z-score of a negative 1.25, and I get the probability. And I see my sign is wrong, so let's change it to the other way around and continue.
So I get a z-score of a negative 1.25. So again, I'm going to draw my distribution, and my mean is still 0.8535 grams. My z-score is now going to be further away from the mean, so that weight 0.8535, this is going to be a z-score of 0, and this is going to be a z-score of negative 1.25, and I want to look for the area above. So again, I'm going to go to my calculator, and so I get this probability to be 0.8944 rounded to 4 digits. So what does that mean? That means 89.44% of the time a sample of 465 M&Ms will have a mean weight of 0.8535 grams or larger. Okay, then the last part says, given these results, does it seem that the Mars company is providing M&M consumers with the amount claimed on the label? So let's look at this, and we know that this is the weight on the label. So if that's going to happen almost 90% of the time, it's not unusual. And so it seems as if the M&M company is providing consumers with the amount claimed on the label,
Or more,
about 89% of the time. That's pretty darn good. So that's how you would do a problem like this. Okay, so now let's look at number 18 on page 321. So it says that women have the pulse rate that are normally distributed with a mean of 77.5 beats per minute and a standard deviation of 11.6 beats per minute. Find percentile 1 and percentile 99. Okay, so let's think about this, and let's do our drawing, and let's start with percentile 1, And remember, the percentile is the percent of the distribution that's lower than that. So P1 would be in the left tail, and the area under that curve would be 1%, which is 0.01. And then P99 would be, or the 99th percentile, would have 99% of the area below. So we could do that. And so that'd be 0.99. Let's go to our calculators and find those.
So now when we use our calculator, let's change it to match that distribution. And to match that distribution, our mean is 77.5, and our standard deviation is going to be 11.6. And we want to find the area to the left, and we want that to be 0.99. Oh, sorry, 0.01 for the P1. And we get 50.5 rounded to the nearest tenth. Now, if we want to get the 99th percentile, we'll put 0.99 there. And when we do that, we get 104 rounded to the nearest tenth, 104.5.
So when I do that, I get P1 is going to equal 50.5 beats per minute, and the 99th percentile will be 104.5 beats per minute. Now part B says sees 25 patients, and let's find the probability that 25 randomly selected women have a mean pulse rate between 70 beats per minute and 85 beats per minute. So that's going to be the sample mean, and we're lower than or equal to 85, and we're greater than or equal to 70. And what I want to do is I want to look at that. I will change them to z-scores. So I'm looking for what's the probability that my z-score will be between 85 minus 77.5 divided by, oops, I've got to go back. It's a sample of size 25, so I know it's normal. The mean is 77.5, but now the standard deviation has changed because we're dealing with a sample. So we need to divide our standard deviation by the square root of 25, which is 5. So for our sampling distribution, our new standard deviation is 2.32. And then on our low end, it'll be 70 minus 77.5 divided by 2.32. Okay.
So now in order to use a calculator, we want to do a between, and we have standardized our scores. So you can see I want to put in a mean of 0 and a standard deviation of 1 to make it a standard normal distribution. I already have my z-scores in there. I'm going to go compute, and you can see almost the entire distribution is between those two z-scores.
Okay, so I've translated my heartbeats per minute into z-scores, and you can see I'm looking for the probability that that's going to be more than 3 standard deviation units from the mean, both on the upper side and the lower side. So we can take this to our calculator and we can calculate this probability. And we get a number that rounds to 0.9988. So about 99.88% of the samples of 25 women will have heartbeats between 70 and 85 beats per minute. Now, Part C says, if the doctor wants to select pulse rates to be used as cutoff values for determining when further tests should be required, which pulse rates are better to use? The results from Part A or the pulse rates of 70 beats per minute and 85 beats per minute from Part B, and why? Well, the doctor wants to deal with individual patients, so it doesn't make sense to use means. It makes sense to use the individuals. So the doctor should use our 50.5 beats per minute and 104.5 beats per minute to make decisions about individual patients. Okay, now let's do number 21 on page 321. This time we're talking about airliners, and we're talking about airline doors. And remember, the airliners have curved bodies, and so they have the door height of 72 inches. Okay, now we're going to talk about men, and their heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. Now, if one male passenger is randomly selected, find the probability that he can fit through the doorway without bending. So A says, what's the probability that an individual passenger will be less than 72 inches tall? And so since it's individual, we will use this distribution. To use this distribution, let's go ahead and standardize the score. And so that would be the same as, what's the probability that Z will be less than 72 minus 69.5 divided by 2.4. Or the probability of Z will be less than 1.04. So let's draw our distribution. So here's our mean, and if it's z-scores, this will be 0. 1.04 will be up here, and we're looking for the area to the left. So let's go to our calculator.
So when we go to our calculator, again, we want to have, we want to do just a standard. And our mean is 0, our standard deviation is 1, and our z-score that we're interested in is going to be 1.04, and less than is the correct direction. And we compute, and we get that probability of 0.8508.
And we get 0.8508. So what that says is that it says 85.08% of men can pass through the door without bending. Okay, now let's look at Part B. Part B says if half of the 200 passengers are men, find the probability that the mean height of the 100 men is less than the 72 inches. So now we have n equals 100, and we want to know what's the probability that the mean height of men is less than 72 inches. And so we're looking at now, we still have a normal distribution. Our mean is still 69.5, but now our standard deviation is being divided by the square root of 100. So that's the same as a normal distribution with a mean of 69.5 and the standard deviation of 0.24. So again, let's draw our distribution. And let's go ahead and standardize our score. But now we say we want the probability of z to be less than 72 minus 69.5 divided by 0.24. When we do that, we get the probability that z will be less than, we get a z-score of 10.41. Now, if you, or 10.42, if you go to your table A2, you're not going to find a z-score of 10.42. This is just huge. Just huge. But 10.42 is a huge z-score. Let's take it to our...
So when we take it to the calculator and we put in a z-score of 10.42 and calculate our probability, it's 1. The z-score was huge, the probability is huge.
The calculator says the probability is 1. Yes, everybody's on average will be short enough to go through there. So 100% of the means, the mean height of groups of 100 men will be below 72 inches. Okay, now let's do C. Okay, so now let's look at Part C. When considering the comfort and safety of passengers, which result is more relevant? The probability from Part A for individuals or the probability from Part B for a sample? Why? Well, the probability from Part A is more relevant because it shows that 85.08% of the male passengers won't need to bend. And the result from Part B gives us information about a mean for a group of 100 men, which the mean for the group in this case doesn't give us useful information about the comfort and safety of individual male passengers. Let's look at Part D, and when we did this problem, we ignored the women. And why would we do that? Well, because men are generally taller than women, a design that accommodates a suitable proportion of men will also accommodate a greater proportion of women. So in this case, because we're dealing with height and men are taller than women, we can ignore the women. Not always, just in this case.